Hello, my name is Jacob Farley, and this is Lab 2 on projectile motion. In this lab, we observe a falling object as it's moving in the horizontal, and we compare the observed and computational models, including and excluding the drag force. The object that we used was a balled-up sheet of paper. We tracked its position using the tracker software, and we created our computational model for the predicted position via GlowScript. This lab demonstrates the effect of Newton's third law, creating the drag force, and the importance of the drag force in calculations. The fundamental principles that we use in calculations have been Newton's second law, F equals ma, gravitational force, and drag force. For the observed motion, we had somebody toss a paper ball forward with meter sticks so that we could clearly see and identify using the tracker software how far the ball traveled. And tracker output these graphs and tables. For the computational model, we used the same initial conditions that we observed from the tracker model, and we gave the ball a mass of 5 grams. G is equal to negative 9.8, and with no drag, we made B equal to 0. We calculated the net force to just be negative 9.8 once it's applied to the velocity in the equation, so mass cancels out. And inside of a while loop, we update the velocity and the position of the ball to create this trajectory. So as it increases in the x direction, it decreases in the y direction at a rate equal to the force of gravity. So the computational model with drag had all of the same initial conditions, except we had a b value that we found to be 0.005. We walked through the math of finding the drag force, plugging into the equation, and we added it to the gravitational force. And then once we added it together, we multiplied it by delta t and divided by the mass of the ball to get acceleration instead of force in order to update velocity, which updates position, which gave us this slightly more curved trajectory graph. So in summary, both computational models were somewhat similar to the perceived motion, especially at the beginning. But the computational model, including drag, was almost exact throughout the entirety of it, while the other model was skewed. Some possible errors could be from outside forces like blowing air and general air movement in the room, which could have exerted other forces on the ball past a stagnant drag force. Imperfections in air resistance, such as the ball was not perfectly spherical, or which causes the air to impact different parts of the ball in different ways. And finally is human error. We recorded at an angle which can skew the tracker program, and the low quality of the video caused the auto tracker not to work, meaning that I had to input the position of the ball on each frame manually. And some questions would be, what if the medium was a denser gas or liquid? And if it was a different medium, the coefficient of drag B would change, likely significantly, and this would account for the increase in drag force and the slower or faster movement of the object. What happens to terminal velocity if the ball is thrown downwards? Initial velocity does not affect terminal velocity. Depending on the strength of the throw, the ball would have reached terminal velocity more quickly or initially blown by it, causing the drag force to outweigh the gravitational force until the object reached terminal velocity. Finally, we can conclude that the drag force is not negligible with items as light and large as the paper ball used in this experiment. It's incredibly important to factor in if you want precise results.